To deploy a database application on one of the major public clouds like Amazon EC2, you can provision a compute instance, which is typically a virtual machine that has a certain amount of CPU cores and memory. So in this resource model, the major deviation from the traditional model is the storage. So instead of being physically attached to your compute instance, storage devices are disaggregated. They together form an independent system that provides storage services to your compute instance over the network. And another important feature is that the application data stored in this disaggregated storage, disaggregated disk is also replicated to avoid any data loss. So this gives us two important properties about disaggregated disks. And first is that they are highly available because they are never attached. So they can basically be accessed at any time by anyone. And the second is that they're highly durable because due to replication. So this begs the question, can high availability at the disk level be easily translated to high availability at the application level? So in that spirit, practitioners have already started adopting a new fault tolerance technique that leverages disaggregated disks. So when the primary instance of the application is deemed failed, since we can still access the application disk, we can basically spin up a new backup instance, move over the application disk from the failed primary to the new backup to restart the application from the same application data. And we call this recovery from disaggregated storage, shown as red. So basically, when failure occurs, a newly spawned backup instance recovers application state from disaggregated storage and continues serving the application. So compared to the traditional application level replication that requires multiple replica instances of the application, such as primary backup replication, RED only requires one running instance at all times, bringing significant savings on capital costs. RED is also generally applicable to any crash-consistent application. So crash consistency is basically two requirements. One is that before externalizing any application state change, updates related to those changes must be persisted. And the second is that the application needs to be able to recover from the crash using techniques like red hat logging. Unfortunately, RED does not bridge the gap between disk high availability and application high availability. And the first reason why RED has low availability is that the failover must be sequential. So RED has two major recovery steps, failover steps. Step one, failure detection on the primary to determine whether the primary has truly failed by using a timeout. And step two, recovery on the backup, which basically includes moving over the disk and restarting the application. So RED must proceed with the two steps sequentially, meaning that step two cannot start until step one is completed. And this is because both the primary instance and the backup instance require exclusive access to the same application disk. And this basically gives RED a hard decision to make, and that is, when should we consider step one to be completed? Or in other words, how long should the timeout be? And such a decision is a fundamentally hard one, because the future is unknown. So when the primary stops responding, what is happening? Has it truly failed, or this is just a network blip and the primary can come back shortly after? And if that's the case, how long should we keep waiting to see if the primary self-recovers? And on the backup side, if we decide to do a failover, then the question is, how long does the recovery on the backup take? It could take just a couple seconds to even several minutes, depending on the application state at the time of failure, which may require fixing corruptions and replaying transactions. So if we use a short timeout, we may commit to a long recovery when the failure situation on the primary is only transient, meaning that simply waiting for the primary to come back will be a lot faster. If we use a long timeout, then we effectively slow down the system's reaction to true failures. So how long the failure detection timeout should be is a fundamentally hard decision, because no matter if it's long or short, there is always an opportunity cost. So now suppose we have an oracle model that does know about the future. What's the best we can do? So right when the primary instance stops responding, the oracle knows that it would take, say, 30 seconds for the primary to come back. And meanwhile, it would take only 20 seconds for the recovery to finish on the backup if we initiate failover right away. And clearly, the optimal decision will be to simply go with the faster one. And in this case, the oracle simply immediately initiates recovery on the backup without waiting. And if otherwise the recovery is longer, then oracle simply waits for the primary to come back. So this is saying that with the oracle model, the need for using a timeout is eliminated completely. So in that spirit, we propose speculative recovery that makes a similarly optimal decision in practice without knowing the future. So speculative recovery pursues both paths in parallel, meaning that the backup is doing recovery while still waiting for the primary to come back. And speculative recovery simply goes with whichever completes first. Speculative recovery achieves this. To achieve this, when the primary stops responding, speculative recovery immediately creates an independent clone of the application disk and attaches it to the backup instance to start recovery, while the primary instance is not interfered with to allow you a chance to come back in parallel. So this basically creates a race between the primary instance and backup instance. It is going to be either the primary becomes available again first, or the backup completes recovery first. And we believe that in theory, the model of speculative recovery achieves the same results as the oracle model by letting the two paths play out and observing which one is the faster one. So for the rest of my talk, I will give a more detailed introduction to speculative recovery, which is enabled by this novel concept of disk superposition. And next, I will talk about two new primitives, super and collapse, that were introduced that can be used to implement a speculative recovery system. And finally, I will present some key evaluation results and conclude. So by parallelizing the primary instance and the backup instance, the application state diverges. That is, the application now has two independent versions at the same time. So to ensure correctness, speculative recovery must ensure that only one of the versions can ever be observed by external clients. And this is basically a superposition where the application disk is allowed to diverge to two versions at the same time, only temporarily, as long as neither is observed. And when one of the versions is observed, the other version must be destroyed as though it never existed. So the concept of superposition is originally from quantum physics, and the famous illustration is the Schrodinger's cat experiment. So, where the cat is both alive and dead at the same time. So to draw an analogy, when the primary stops responding, in the client's perspective, it's just like putting the system inside a Schrodinger's box. And inside this box, very similar to a cat being both alive and dead at the same time, in our scenario, it's both the primary instance and the backup instance being alive at the same time. And when the box is opened, it is going to be either, the primary has been there the whole time, there was no backup at all, or the backup has already taken over right when the primary stopped responding. So we say that a superposition is created when a clone of the application disk is created, and a superposition is collapsed when one of the disk version is observed. For creating a superposition, the biggest challenge is how to make a disk clone fast to create as well as performant, because bad performance on a disk clone may significantly increase the time to finish recovery on the backup, which would neutralize any benefit from parallelizing the two instances. And copy on write is a common technique that can be fast to create a clone, but it provides bad I/O performance after creation, especially under highly parallel write workloads, such as during recovery. For collapsing a superposition, the biggest challenge is to make sure that only one of the versions can ever be observed. And to achieve this, speculative recovery monitors write to the primary version of the disk. So basically, when a write is applied on the primary disk after entering a superposition, speculative recovery determines that the primary instance has been observed because that write may cause observable application state change. And in this case, the superposition is collapsed by aborting recovery on the backup to make sure that it cannot be observed. If otherwise, we see no writes until when the recovery on the backup completes, then the application state on the primary has not been changed. Then the superposition is collapsed by promoting the backup to be in the new primary and deallocating the old primary to make sure that it cannot be observed. Now let's talk about how to implement a speculative recovery system. So we introduce a set of primitives, super and collapse. Basically, super creates a superposition by creating a disk clone. Collapse collapses a superposition by monitoring which disk version has been observed. So super uses copy and write to create a clone. It's fast to do so because the actual data copying is delayed. But also such delaying hurts I/O performance after creation. And our experiments show that on some existing copy and write implementations, the average write latency could be 30 times higher. And to provide explanations, we instrumented the open source distributed storage system Ceph and discovered two major reasons. One is that concurrent copy and write operations are forced to be serialized due to bottlenecks at the allocation table. And the second reason is that data copying often happens over the network instead of local, because this is a distributed system. And we proposed co-located clone to solve this problem, and it brings the I/O performance of a disk clone very close to a regular disk. And please see our paper for more details. And okay, now collapse. So collapse uses a dirty bit to monitor writes to the primary disk. So the dirty bit is basically a piece of metadata for the primary disk. So basically, when entering a superposition, the dirty bit is reset, and any write following that point will set the dirty bit. So a call to collapse checks the dirty bit, and then decides what to do with the failover. So basically, if it's dirty, then we must abort recovery and continue with the primary. And if it's clean, then we can proceed with promotion and continue with the backup. And also, please see our paper for more details. So this is an overview of the system. So there are three components concerning a speculative recovery system: the instance pool, the disaggregated storage ledger, storage cluster, and the failure monitor. So when the primary instance stops responding, the failure monitor initiates speculative recovery by spinning up a new backup instance, calling super to the storage cluster, which causes the application disk to enter a superposition. And the storage cluster also starts tracking writes to the primary version of the disk. And when the recovery on the backup instance completes, the failure monitor calls collapse to determine which instance should continue serving the application based on the value of the dirty bit. And finally, I will present some key evaluation results to show the practical availability improvements. We implemented a prototype speculative recovery system called SpecReds based on Ceph's block interface called RBD. We used Docker containers for the instance pool and NVMe SSDs for the storage cluster. So first, to show the point that co-located clone achieves close to normal I/O performance, we compare three types of disks: a regular RBD disk, a clone disk with Ceph's existing clone implementation, and a clone disk with co-located clone for super. And to show the end-to-end availability improvement, we compare three systems: the baseline system Reds, which is using a regular disk, our system, which is using a disk clone with super, and the Oracle model, which is using a regular disk as well. We compare three database applications: MySQL, Postgres, and MariaDB. So we start by looking at the application recovery latency from various disk states. Here are the three disk types that we mentioned. On the x-axis is the disk state represented by two parameters. So the letter on the left is the failure type. So we emulated two types of failures. A clean failure that allows for some cleanup by synchronously stopping the Docker container, and an unclean failure that injects a kernel panic without any chance for cleanup. And the number on the right is the size of the database write-ahead log. And on the y-axis is the recovery latency. So here we have the baseline, a regular RBD disk. We can see that an unclean failure indeed takes longer to recovery. And a larger write-ahead log also requires more recovery work. And when we're doing recovery on the clone disk with Cephe's existing implementation, you can see that the recovery latency is significantly higher. This is basically when you have the write latency be 30 times higher, application recovery suffers. And finally, super is very close to the regular disk, while significantly outperforming Cephe's existing implementation. And finally, how does the recovery latency translate to end-to-end availability improvement? And to show this, we divide the failover scenarios into four broad categories based on the length of timeout and recovery. So we pick 1 minute and 5 seconds for long timeout and short time respectively. And just to clarify, this timeout is only for REDs because SpecReds and Oracle, they do not need to use a timeout. And on the x-axis is the recovery length. We also use 1 minute for long recovery and 5 seconds for short recovery. And on the y-axis is the failover latency, which is a simple simulation by adding timeout and recovery together. So first, for long timeout, we can see that SpecReds reduces the failover latency significantly because it does not need to wait for a timeout. And for a short timeout, we can see that REDs and SpecReds have very similar latencies because a short timeout allows REDs to initiate failover much sooner. And in fact, in some cases, SpecReds is even slower because it operates on a slightly slower disk clone. But as we discussed, the problem with using a short timeout is that it risks committing to a long recovery unnecessarily. So to show this, we simulated a false positive failure where the primary comes back after 10 seconds of being unavailable. And in this case, REDs using a 5-second timeout would trigger a 1 minute long recovery, while SpecReds can abort recovery when the primary comes back after 10 seconds. So SpecReds avoids unnecessary failovers. So to summarize, SpecReds saves a lot on long timeouts, while it also avoids unnecessary failovers compared to REDs using a short timeout. So to conclude my talk with one sentence, speculative recovery safely and efficiently parallelizes self-heal on the primary and recovery on the backup to push failover latency to the lower bound of REDs. Thank you. That's it. Thank you.